So today we're pleased to have Dr. Lisa Rodenburg, Professor of Environmental Science at Rutgers University, as our presenter. Dr. Rodenburg is an expert on PCBs and pigments and how they are dispersed into the environment via their use in consumer products. A lot of her work involves using data sets that involve entire watersheds to understand the sources and fate of persistent organic pollutants. So please welcome Dr. Rodenburg.
Thank you. Hello, everybody. Thank you for joining us here today to talk about PCBs. I've been here at Rutgers for 19 years, and those 19 years I've spent studying PCBs and other chemicals, chemical contaminants in the environment. So I hope that you'll get something out of today's presentation. It's intended sort of at the general introductory level. But even if you know something about PCBs, I think you'll find some new information because I've tried to update this with some of the new stuff that's coming out about PCB sources and toxicity. So PCBs are polychlorinated biphenyls. And so you can see the little blue picture there of what the polychlorinated biphenyl molecule looks like. It's just two benzene rings stuck together. And then that leaves 10 different positions open where you could add a chlorine or one or more chlorines to the benzene ring. So the PCBs can have up to anywhere between 1 and 10 chlorines. And because those chlorines can be on different positions in the ring, you end up with 209 different PCB molecules. So first lesson to learn from this is that PCBs are not a chemical, they are a class of many chemicals. Again, there's 209 of them. And this is one of the reasons why measuring PCBs is really tricky. It can be quite difficult sometimes because there's 209 different chemicals you're trying to measure, and they're very similar in structure and properties. So a group of congeners that all has the same number of chlorines is called a homolog group. And in the United States, PCBs were sold under the trade name Arichlor by Monsanto. Monsanto was the only, or virtually the only manufacturer of PCBs in North America. And they sold them under the trade name Arichlor. They had many, many uses. They were used in electrical equipment primarily, including transformers and capacitors, but they had many other applications as well, which we'll talk about in another slide or two. They have very high dielectric property, which is what makes them great in these electrical equipments. And they're very flame resistant, which was important because if you did have, for example, a fire at an electrical substation, it was really good that the PCBs were flame retardant so that if all these transformers and capacitors were involved in a fire, the PCBs wouldn't light up. They wouldn't contribute to the problem. So the problem, of course, is that PCBs were found to be toxic. And you can very legitimately ask the question, why were we selling a bunch of chemicals that were toxic? Why didn't we not sell them in the first place? But unfortunately, under the rules at the time, the way that the law was written in the United States, it was acceptable to sell chemicals in commerce that were toxic. And it wasn't until it was discovered how toxic PCBs were that the U.S. Congress moved a bill forward to ban them. And so they were banned in 1976 under the Toxic Substances Control Act, often called TSCA. And at that point, their manufacture ceased and they stopped being used. But because they're quite persistent, here we are in 2017 still talking about the problem of PCBs 30 years later. So about 1.3 million metric tons of PCBs were produced worldwide. It's tough to really get a handle on that number, but it's a big number. And the problem with that number is it means that there's PCBs all over the United States. PCBs can travel through the atmosphere. They can travel with water or soil particles. And so unfortunately, PCBs are present pretty much everywhere in the United States. So when PCBs were used, they had, some of them were used in what were called open applications, meaning that it was easy for the PCBs to get out of that application and into the environment. And then there were other applications that were considered to be closed. So the open applications were banned first, obviously, because those were the ones that had the greatest potential to release PCBs into the environment. And so that's, you can see, it's a large list here: flame retardants, inks, adhesives. The microencapsulation of dyes for carbonless duplicating paper is a big part of the reason why every recycled paper mill in the United States has a big problem with PCBs, because the PCBs were present in this carbonless copy paper, and when that paper gets recycled, the PCBs get into the recycled paper stream. Paints, pesticides, plasticizers, all kinds of stuff, surface coatings, metal coatings, wire insulators. Every ship built by the Navy that had any kind of wire in it, which was every ship built by the Navy, had PCBs in it. So when the Navy goes to break down these old ships, they have to do something about the PCBs. So those open applications were banned in 1974. The closed applications were allowed to continue for a little bit longer. And that includes, again, capacitors, transformers, and the kinds of hydraulic fluids that are contained within the equipment. But unfortunately, for example, transformers, they do leak. They do leak over time. And certainly transformers that were built in the 1970s and contain PCBs, if they're still in use, they're getting pretty old. And unfortunately, that means that they are starting to leak more and more. So even though these are quote unquote closed applications, they do have the possibility of releasing PCBs back to the environment. So the problem with PCBs is that they have the trifecta of bad things, right? They are persistent, meaning that they don't break down readily in the environment. They're toxic, and they bioaccumulate in organisms. And what we mean by bioaccumulate is that as you go up the food chain, and that's what this picture is intended to tell you, that at the bottom you have the algae. Algae might take up PCBs passively through just diffusion into the algae from the water. But then when the shrimp eat the algae, they take everything that was in all the algae that they eat, and the PCBs in the algae stay in the shrimp's body. Even though the rest of the material might get pooped away, the PCBs stay in the organism's body. And so then as you move up the next layer of the food chain to the fish and then the seals and then the polar bears, they're taking large amounts of PCBs consumed in the food and concentrating them in one organism and in the fatty tissues of one organism. So as you go higher up the food chain, you can build up very high levels of PCBs. So those three properties taken together are what make PCBs such a problem. If they were toxic and bioaccumulative, but they weren't persistent, maybe they wouldn't be a big deal because they would have broken down by now. But it's the fact that you have all three of these things going on in one chemical that makes them such an issue. So we've said many times now that PCBs are persistent, but it is true that they do have some pathways by which they break down. The heavy congeners, and what I mean by heavy is that they have a lot of chlorines on them. The heavy congeners can get dechlorinated by bacteria. Bacteria will pop off the chlorines. And then once you remove a bunch of chlorines and you get down to the congeners that only have one or two chlorines on them, then they can be degraded aerobically by bacteria. And they also are then more volatile because they're less heavy. They don't have all these heavy chlorines on them anymore. So they're liable to get into the gas phase. And once they're in the atmosphere, there are hydroxyl radicals and other reactive species in the atmosphere that will break down some of the PCBs. So there are some ways by which PCBs can be destroyed in the environment, but they're slow. And compared to the large volume of PCBs that's existing out there, they're not fast enough to really make a big dent in the amount of PCBs circulating in the environment. So here's an example of the aquatic food chain, and this is very similar to the one I just showed, where the polar bear was the apex predator. But this is making very clear that it's really human beings that are the apex predator in most of these environments. Excuse me. It's ragweed season. So in many of the environments we're talking about, humans are the apex predator, which means that humans can develop very high levels of PCBs in their body tissues. And that's one of the reasons why PCBs are a problem. So they're a problem for, human health. They're also a problem for environmental health because the fish and the birds and all of these things are also being exposed to PCBs. So there's a range of environmental and health effects that we have to worry about with PCBs. And so this is a couple years old now, but I have no reason to think that the picture has changed here. These are the causes of impairment listed under the Clean Water Act for water bodies all across the United States. So this is all of the water bodies in the United States that are considered to be impaired. This is a list of what are the top reasons for impairment. And you can see the first few: pathogens, mercury, metals, nutrients, low dissolved oxygen, sediment, and then you get to PCBs. So in terms of organic chemicals that are problematic in terms of their environmental impact, PCBs really rise to the top. They are the top driver of toxicity and problems at Superfund sites all over the country, from the Upper Hudson River Superfund site to the Duwamish River, which I've been working in lately, to the Portland Harbor Superfund site, to the Houston Ship Canal, all over the United States. PCBs are one of the main causes for water quality impairment and toxicity in harbors and waterways all over the U.S. So PCBs are toxic, as I mentioned. In the last, since PCBs were banned in the 70s, most of the focus when thinking about the toxicity of PCBs has been on the PCB congeners that have 4 or more chlorines. And the reason that those were the focus is because they're heavy, and that makes them very hydrophobic. They like to stick to fatty tissues, and therefore they bioaccumulate really readily in your body. And so this list of things, liver, thyroid, dermal changes, immunological alterations, neurodevelopmental changes, meaning that they affect children, and children are exposed to PCBs through the placenta and also through breast milk, reduced birth weights, cancer. So there's a lot of health effects. And most of the study of these health effects is really focused on the heavier congeners with more chlorines. It's only in the last maybe 10 or 15 years that people have started to think about the congeners with only 1 or 2 chlorines. And it turns out that those don't bioaccumulate like the heavy ones do. They tend to sort of pass into your body and then pass right out again. But what we're discovering is that alone doesn't mean that they're not toxic and that they don't have real bad effects. And so they can get into your body, they can become hydroxylated through the cytochrome P450 system, and they can end up making hydroxylated PCBs, which are really, really toxic. So the health effects of PCBs run the gamut from the high molecular weight congeners to the low molecular weight congeners, affecting many different organ systems in the body, the immune system, the reproductive system, and they have particularly bad effects on children. And again, children can be affected through breast milk and through placental transfer. And as we'll see toward the end of this webinar, I'm going to spend a few slides talking specifically about the issue of PCBs in schools, because it's a really big problem right now. It's emerging as a big public policy problem in the United States. So we'll talk about that more toward the end. So how do you get exposed? Most people in the United States, their major route of exposure to PCBs is the eating of fish. Fish that have been caught in contaminated waterways. When you go to the store, you don't always know where your fish are coming from. And sometimes those fish have been caught in contaminated waterways. And so you are taking in PCBs as you're eating the fish. And for most people in the United States, that is the major route of exposure. Now you can also be exposed to PCBs through inhalation. Obviously, that's only going to be a problem if you're perhaps working in a building that was built with PCBs in the building material. And again, we're going to talk about PCBs in schools toward the end. So inhalation can be an important route of exposure if you happen to work or live in one of these buildings. And there is the possibility for dermal absorption. And again, if you happen to work in a building that's contaminated and you have children who are running around touching all the contaminated caulk and adhesives and things that were used to build the building, they can absorb PCBs through their skin. The dermal absorption was also a big problem with the carbonless copy paper, because you know how people are always touching their mouth and then leafing through pages of documents. That hand-to-mouth contact was resulting in a lot of exposure of PCBs through carbonless copy paper. So, and the point here toward the bottom of the slide is that because I'm using the term here, POPs, persistent organic pollutants, of which PCBs are one type of persistent organic pollutant, because they bioaccumulate, it really doesn't matter how you're exposed. Once the PCBs get into your body, they stay there, and it's difficult to get rid of them. So it doesn't really matter what the route of absorption is. Once they're in your body, you are exposed, and you're probably going to carry that PCB burden around with you for the rest of your life. So in the United States, we have federal water quality standards established for protection of human health and the environment. And the federal water quality standard for PCBs is 64 picograms per liter. Now, states are allowed to set their own water quality standards. And if they can prove that, for example, the people who live in that watershed just don't eat very much fish, then they can actually set a higher water quality standard than that. That, for example, is what happened in the Houston Ship Canal area. They have a water quality standard of 885 picograms per liter. But in the Delaware River, they did a fish consumption survey, and they showed that people in the Delaware River region eat a lot of fish. And so their water quality standard is it's only 8 picograms per liter instead of the 64. So these can change by location. But this is a very, very low number. In fact, this is almost unmeasurable. It's so low. We'll talk about analytical techniques for measuring PCBs in a second, and this is a really low number that can be quite difficult to measure. So that's just a function of how toxic the PCBs are, that the amount that is considered quote-unquote safe in the water is such a low number that you can barely measure it. So here's an example of the Delaware River. Remember that the federal water quality standard is 64 picograms per liter, but in the Delaware River, you're looking at 2,000, sometimes as much as 5,000 picograms per liter. And the Delaware River is really not even that contaminated in terms of U.S. rivers. It's kind of a normal industrial, river in the United States. There are other rivers that are much worse. So I use the Delaware as sort of a general example of the kind of thing you can expect in any urban area. So we are, at least 2 orders of magnitude away from being able to achieve these water quality standards in many urban areas of the United States. And trying to bring PCB concentrations down by a factor of 100 is really tough. It's not easy to get 99% source control. It's very difficult. So how do you measure PCBs? The method that has been used the most and has the longest history is called EPA method 8082. It's been around since the 1970s, and any old documents that you read of PCB measurements that were conducted before about the year 2000 would all have been conducted using EPA method 8082 or something similar to it. It uses gas chromatography with an electron capture detector. So that's kind of an old technology. It's been around for a while. And usually when you measure PCBs by method 8082, you're usually not trying to measure individual congeners. Remember, we said that there's 209 different congeners, and it's tricky to measure all 209. So instead, with this older method, usually what they do is they measure aerochlors. They say, okay, well, I don't know exactly what the congener composition is, but it kind of roughly looks like aerochlor 1260, for example. And then they'll report a number, a concentration of aerochlor 1260. The detection limits are in the part per billion range, and that 64 picograms that I was talking about before, 64 picograms per liter is in the part per quadrillion range. So this EPA method 8082 couldn't get down low enough to even measure the water quality standard that exists these days. And these days, it depends on the lab that you go to, but you can usually get method 8082 run on your samples for maybe $200 a sample. So it's not cheap, but it's not ridiculously expensive. There are some less sensitive methods, and the main one is called ELISA. ELISA is an acronym that stands for Enzyme-Linked Immunosorbent Assay. And essentially what you do there is you train the bacteria to have an immune response to whatever chemical you're trying to measure. And they use ELISA kits for all kinds of things, PCBs, dioxins, metals, all kinds of things. You can train the bacteria to have this immune response. And the immune response causes the bacteria to glow, and then it's just a visual thing. It's a spectrophotometer thing that you can just measure the intensity of the light coming out of your sample. So it's quite cheap to do. It's quick and kind of a quick and dirty screening technique to see if you have a big PCB problem. It'll measure total PCBs, not individual congeners, but the sum of all 209 PCBs, or could also in some cases measure aerochlors. But the detection limits are up in the part per million range, so they're not great. So this is really just a screening tool. But the advantage, as you can see, is it's roughly $20 a sample. It's quite inexpensive. So sometimes people use this as a screening tool to rapidly test, hundreds of soil samples, for example, to try to find where the hot spots might be in terms of PCB contamination. So the new thing that's come along for the measurement of PCBs is the new EPA method 1668 that came out in 1999. And it has become pretty widely adopted. EPA is requiring the use of method 1668 at most of the big Superfund sites and most of the sites where PCBs are a problem now. It uses gas chromatography, but it uses a high-resolution mass spectrometer. A high-resolution mass spectrometer is a piece of equipment that costs about $1 million, and you need to pay somebody like $80,000 a year just to run it, keep it running effectively. So it's a very expensive piece of equipment, but it can individually measure most of the 209 congeners. You can measure all of them. It's just that some of them coalute with others, and so that you sum them together and say, well, this peak on the chromatogram is these 5 congeners together. I don't know how much of that peak is congener A versus congener B. But it does much better in terms of measuring individual congeners than the old 8082 method. And the big advantage is the detection limits are now getting down into the part per quadrillion range. So that's the range where you can now actually measure PCBs down at the range where the water quality standard has been set. But the problem is it's expensive. It's like $900 per sample, depending on, again, you could probably shop around and get a cheaper contract lab, but a good contract lab will charge you about $900 per sample. And by the way, not all contract labs could do a great job with this method. Some of them will take your money and then give you some data that's not so great. So it's worth it to pay the money to get a good, reliable contract lab. So the invention or the development of method 1668 really was a game changer, because now we can start to measure PCBs in places where we didn't even think there were PCBs before. We can get a lot more information about what the sources are, because we can look at individual congeners. And, you know, for me as an environmental chemist, I feel that's a great thing. I'm really happy about it. But you know, if you're running a contaminated site, you might not be so happy because now you're suddenly finding contamination everywhere. And you were hoping maybe it was just localized to one place on the site. So it's been a two-edged sword. Method 1668 has really changed the way people measure and think about PCB contamination. And it's really important to point out that the old Aerochlor method, this is data from the Hudson River, from the U.S. Army Corps of Engineers, and they did a subset of samples, there's maybe 30 samples here, where they measured PCBs in the sample using the Aerochlor method, the 8082 method, and also using the 1668 method. And when you plot one versus the other, it's not a great agreement between the two methods. The R-squared is only 0.4 and the slope is not 1. So if these two methods were giving you exactly the same data, the slope would be 1, the intercept would be 0, and the R-squared would be, you know, 0.9. So there's a lot of disagreement, and that's pretty upsetting, because in a place like the Upper Hudson River, you know, General Electric has spent $500 million, billion with a B, dredging the river based on data that, you know, we're not really sure how accurate it is. Okay, so as I mentioned, you have all these individual PCB congeners, and on this particular plot, those are shown across the bottom. You know, 8 plus 5 means PCB 8 plus PCB 5. I can't separate the two, so I'm just going to quantify them together. And then on the y-axis, you have the percent in the Aerochlor. And this is a plot for Aerochlor 1254. It's one of the many formulations that Monsanto was manufacturing. And so the first point is, you see how there's sort of a Gaussian distribution here. We have a lot of high bars in the middle and low down at the ends. And in this plot, the congeners are listed in you know, from just lowest number to highest number. And the way the numbering works is the lowest number has only 1 chlorine, and the highest number, PCB 209, has 10 chlorines. So as you go from left to right, you're increasing the molecular weight of the congeners, and you're increasing the total number of chlorines on the molecule. So Aerochlor 1254 has, you know, kind of this rough distribution of PCBs, mostly penta, you know, PCBs with 5 chlorines on them. And what I'm trying to point out here is that the size, the number of chlorines on the molecule, has a big impact on the physical properties of the chemical. So PCBs with only 1 or 2 chlorines, they're lighter in the sense that their molecular weight is lower. And therefore, they're quite volatile. Their vapor pressures are pretty high. They can volatilize into the gas phase and blow away with the wind. They're also less likely to bioaccumulate because they're more soluble in water. You can remove them from your body through your urine, for example, and they're not as liable to stick to your fatty tissues. Whereas on the other end, the heavier congeners with more chlorines, they would prefer to stick to solids or to fatty tissues. They're not going to particularly be in the gas phase, and therefore they bioaccumulate more effectively. So it's important to understand that, you know, again, we have 209 congeners, and they run the gamut in terms of their physical and chemical properties. Some of them are quite volatile. Some of them are very, very hydrophobic and are going to stick to fatty tissues. So the main sources of PCBs in most watersheds in the United States are the Aerochlors that were produced by Monsanto. Their fingerprints can change a little bit, so sometimes it's hard to identify, you know, if it started out looking exactly like the Aerochlor, then over time it might change a little bit. It doesn't exactly look like the Aerochlor anymore. But that is the main source because, you know, as we said, 1.3 million metric tons of PCBs produced. It's a lot of PCBs out there in the environment. Most of them were produced intentionally for sale on the market. But there are a couple of sources of PCBs that have started to become proportionately slightly more important over time, because over time, all of these Aerochlor type PCBs are slowly exiting our environment. One way or another, they are slowly being buried in deep sediments of the ocean, or they're volatilizing away with the wind. And so the overall levels of PCBs in the environment are dropping. And as the Aerochlor type PCBs are starting to go away, we're starting to be able to see more and more some of the non-Aerochlor sources. And many, I'm going to talk about what some of the categories of non-Aerochlor sources are, but a lot of them have to do with different pigments. And then I mentioned earlier that there is one method by which PCBs can be destroyed in the environment, and that is through bacteria that like to remove some of the chlorines. And so if you go out looking for a PCB source, you might find something that looks like a dechlorination signal. It's the product of the dechlorination of these PCBs by bacteria. And so it doesn't look like the original Aerochlor anymore. Now, it probably started out life as an Aerochlor because that's what the bacteria were feeding on, but it has altered its fingerprint. It looks very different than it did from the original. So we're going to talk about each of these in turn. As I mentioned, the Aerochlors. Aerochlor was a trade name used by Monsanto. It was the only North American producer of PCBs, and it produced a whole number of different formulations with different numbers. I mentioned 1254 in that previous slide. They also produced 1242 and 1260, and the numbering convention was that the 12 stood for the 12 carbons on the PCB molecule, and then the 42 or the 60 or whatever stood for the percent of the formulation that consisted of chlorine by weight. So they would take a big vat of biphenyl and throw in 42% chlorine and let it all react, and then that would be their Aerochlor 1242. And then later on, when it started to become clear that PCBs were environmentally problematic, they dreamed up something called Aerochlor 1016, and that name doesn't really have any meaning, but it was very, very similar to Aerochlor 1242, except that they tried to remove some of the higher molecular weight congeners because they knew that those were bad. So those are some of the typical Aerochlor names that you might run into if you're, for example, looking at a contaminated site or something. You'll see some of these. These PCBs produced by Monsanto, as I mentioned, they were used in all kinds of consumer products and transformers and capacitors and carbonless copy paper and in building materials. And so they've dispersed all over the environment. And every city in the United States has some kind of PCB problem. To a greater or lesser extent, we've all got PCBs, every city in the US. And some cities, especially on the West Coast, have spent fair amounts of money trying to combat PCBs, and they have decided that they shouldn't have to pay for that. And so they have sued Monsanto over its production of PCBs. And that includes, again, Spokane, Portland, a bunch of cities in California, and the entire state of Washington. So this is kind of a new development. I believe that this came about in the last 2 years or so. And so that's a pretty big change. In the past, I think Monsanto had kind of gotten away with it to some extent, but now there's these different lawsuits pending. So here's an example of what the different Aerochlors look like. These are the 4 big ones. I remember I mentioned that Aerochlor 1016 looks a lot like Aerochlor 1242, so they're very similar, so I've lumped those together. And then there was Aerochlor 1248, 1254, and 1260. So these 5 Aerochlors made up 99% of all the US production. There are a couple of others. There's Aerochlor 1268 and 1272, but those were very, very minor, rarely used, not the kind of thing that you're typically going to run into when you're doing any kind of site assessment or thinking about PCBs. So this is what they look like, and you can see, Aerochlor 1242 was only 42% chlorine by weight, so its congeners are kind of bunched up there on the left because those are lower molecular weight. Whereas Aerochlor 1260, was 60% chlorine by weight, so it has a lot more of the heavy congeners, so they're all the way over there on the right with the really heavy stuff. And the point here is that if you do measure all these individual congeners and then you plot them up in a graph like this, you can compare what you're measuring out of the environment to what was measured in the original Aerochlor samples, and you can get a pretty good idea of what Aerochlor it is that's out there in the environment. And then based on knowing on which Aerochlors were used for which types of applications, which industries, then you can start to figure out who's responsible for the PCB contamination that you're seeing in your local waterways. I mentioned that the PCB congener patterns can change a little bit over time. And there's a number of ways that this can happen through evaporation and condensation of PCBs, volatilizing into the air and then condensing back down. And one of the other ways that they do get altered is by the organisms. So if these PCBs get into fish, for example, this plot here is supposed to show on the bottom is just a regular, the blue is what was measured in some tissue samples. And this is from Washington State, I believe. And the orange is the Aerochlor, the original Aerochlor unaltered. And you can see on the bottom figure, the blue and the orange bars really match up really, really well. But then on the top figure, the blue bars and the orange bars, there are some places where they really don't match anymore. And I've tried to circle some of those. What's happening there is that organisms go after very specific targeted PCB congeners that for whatever reason fit perfectly into the enzyme and just get destroyed. And so some of the PCBs get left behind, but a few of them just get almost completely removed. I know that the font here is very hard to see, but one of the ones that just disappears is PCB 147 and 172, things like that. They just disappear. So you can get very systematic alteration of the congener fingerprints when you're in biota. And if you know what to look for, you can still relate those fingerprints back to the original Aerochlors. And again, that can give you an idea of who might have been responsible for the PCB contamination in your system. So that's what I'm going to say about Aerochlors. The other big source of PCBs in the environment are these non-Aerochlor sources. And under the Toxic Substances Control Act, the inadvertent production of PCBs was allowed. So if you were running some sort of chemical process and it had maybe had chlorine in it and it had some kind of carbon in it, you put chlorine and carbon together in a chemical reaction, you're going to get some PCBs as a byproduct. And EPA recognized that, and they made no attempt to ban every process in the world that might accidentally produce PCBs. So PCB concentrations in the product have to average less than 25 parts per million. And remember, 25 parts per million is a high number. If you remember back to that slide about measurement methods, that's the kind of concentration that you can measure just using one of those ELISA kits. This is a high concentration. So the average has to be less than 25 part per million, and no individual sample can be higher than 50 part per million. 50 parts per million is a big number for PCBs. If you find anything in the world, anything that you measure that comes up as higher than 50 part per million PCBs is suddenly considered toxic waste and must be remediated. So this is a big number that you see again and again when you're talking about PCBs. But under TSCA, they did something a little odd. They put in these discounting factors that if the PCBs in your formulation only had one chlorine, so they were monochlorobiphenyls, then you could take those concentrations and divide them by a factor of 10. So in other words, you could have an average of 250 parts per million as long as it was just these monochloro PCBs. And if you only have two chlorines on your PCB molecule, you get to discount the concentration by 5. It's kind of an odd thing to do. I think the reason they did it is because they figured that those mono and dichlorinated PCBs are a little less toxic. They don't bioaccumulate as much, so maybe they're not such a big deal. But it does lead to kind of a strange formulation for how you calculate whether your product is meeting or exceeding the standards. But the important point, again, is that TSCA didn't ban this. This was all allowed under TSCA. And as it turns out, there's a number of chemical processes that do produce PCBs. Many different organic color pigments have PCBs in them, especially the diarylid yellows. Diarylid yellow is one of the most commonly used pigments in the world. If you remember your home color printer, it's got a yellow, a pink, a blue, and a black cartridge in it. Excuse me. And that yellow in your home printer is diarylid yellow. It's a very, very common pigment used worldwide. Another pigment that contains PCBs under some circumstances can contain PCBs is titanium dioxide. That's the bright, bright white pigment that's used, for example, in every batch of paint in the world. You go to Home Depot and you buy white paint. It's made white with titanium dioxide, and then they add different pigments to it to make it the color you want. And those can contain PCBs 206, 208, 209. Again, remember the numbering convention. Those are big, heavy congeners with a lot of chlorines on them. And then it turns out that some silicone rubber tubing products also can have PCBs in them. And one of the take-home messages there is that if you are asked to do any sampling for PCBs, don't use silicone rubber tubing to do the sampling. Unfortunately, this has happened too often that people went out and did water sampling, and they used silicone rubber tubing to collect their samples, and the samples became contaminated with PCBs. So this is an example of, this is some work that we did in my lab where we went and we just took samples of newspaper and cardboard and magazines and all kinds of things, and we measured the PCB11 in them, and we found them everywhere we looked, or almost everywhere we looked. That was all stuff from my recycling bin at home. Then we asked all of our friends whenever they traveled to bring us home some paper samples that we could test. And so you can see in the kind of the middle of that figure, there's paper from Georgia and Moldova and China and Costa Rica. And for some reason, the Netherlands had a really high hit for PCB11 in some paper samples that we collected there. So all over the world, these pigment markets are global markets. Most of the pigments are produced in India and China, and then they're sold all over the world. So everywhere you go, you're going to find this PCB11. And the 4-color printing process that I talked about in your home printer, that's the same process that's used to print T-shirts and things. And so we went and we measured PCBs in some T-shirts and some fabric material that were printed with a design on the right, and then some that had no design on them at all on the left. And you can see those that had a printed design, like unfortunately SpongeBob had yellow pigment, and he had a lot of PCB11 in him. So the point is that these PCBs are everywhere. I mean, they're all over in every paper sample that you have, every colored, anything that's color printed, all of these fabric materials, everywhere in the world, they've got some low level of PCBs in them. And we did some leaching tests, and the PCBs do leach out quite readily. So when you wash your clothing, for example, the PCBs and the pigments are going to get out into the waterways. So that's one other source of PCBs that's worth it to be aware of. And then the third, not exactly source, but process by which PCBs can be produced is microbial reduction of PCBs by bacteria. And it used to be that we thought that this only happened in aquatic sediments, like the upper Hudson River was the big example of where bacteria in the Hudson River have been dechlorinating PCBs for years. Ever since General Electric has been dumping PCBs into the upper Hudson River, the bacteria had been going after them. But we found more recently that it can also happen in places like sewers and landfills and in contaminated groundwater. So you can find these dechlorinated PCB signals in a lot of other places. And usually the bacteria, I won't bore you with all the different species names and stuff, but the bacteria that do this, for some reason, they can remove the PCBs on the outer part of the ring, the meta and para positions, if you're looking at that figure on the lower left. Those outer positions, they can remove those chlorines, but for some reason, they can't get into the inner locations, the 2 and 6 positions in the ortho position. And because of that, you get some very characteristic end products, like the molecule that's drawn there on the right. That is PCB number 4. It's got 2 chlorines, both of them in the 2 positions. So we call it 2,2-dichlorobiphenyl. And that is the characteristic end product of dechlorination. So if you do get some 1668 data rolling across your desk and you see a bunch of PCB4 in it, now you know where it comes from. And this is an example of all the different places in the world where we have seen some dechlorination happening, the Delaware River, the different dischargers, so the sewers and the landfills. There was dechlorination happening. New York, New Jersey Harbor, that's dechlorination happening in the upper Hudson River and flowing downstream. The dischargers in the New York Harbor region also showed dechlorination. Again, that's landfills and sewers. The Portland Harbor Superfund site in Portland, Oregon had a ton of dechlorination going on in the groundwater. We also found this in wastewater from Washington, D.C. So the point is that this is happening all over the place. So if you are seeing some strange congener patterns, if someone's asking you to look at some method 1668 data and you're wondering what the heck it is, that could be what it is. Okay, so I'm going to go talk about a couple different case studies, try to give you an overview of different places throughout the United States where PCBs are a problem, and highlight some of the issues here. First, we're going to talk about the Hudson River. I know a lot of people who are watching today are local. You're from the New York, New Jersey area. And so you're probably already aware that the Hudson River is one giant Superfund site for about 30 years, ending when PCBs were banned in 1977. General Electric was discharging PCBs into the upper Hudson River. And it flows from there, from those 2 plants up in Glens Falls, it flows about 200 miles downstream to New York City, and that entire stretch is a big Superfund site. There was a record of decision, meaning that the judge in the case decided on what the remedy would be to clean up the river. And under that record of decision, the remedy was that GE had to dredge portions of the Upper Hudson River, meaning that they dredged the sediment out. And in the case of the Upper Hudson River, I've never heard this happening anywhere else, but in the case of the Upper Hudson River, when they dredged and they brought up this sediment from the bottom of the river, they found pure liquid PCB oil in the river. That's how contaminated it was. So they were dredging up all of this contaminated sediment. They typically, what often happens in these kinds of dredging operations is that the dredging material comes up and it's like what they call black mayonnaise. It's real runny, and it's very difficult to do anything with it because it just runs through your fingers. So what they do is they add cement to it to tighten it up and make it more solid so that they can actually work with it. So they stabilize it with cement, and then they pack it into rail cars and they ship it off to some landfill somewhere that has agreed to take it. And to me that sounds kind of crazy. There's no treatment. There's no attempt to treat the sediment to make it any better. You're just packing it away in a landfill and forgetting about it. But that is the state of the art, unfortunately, when it comes to dredging contamination. So GE has done the dredging. The dredging is now complete. The EPA is saying that now we need, under the Superfund rules, you evaluate the remedy every 5 years to decide whether it has worked or not. And EPA is doing their 5-year reviews and has decided that it's too soon to tell whether the remedy has actually worked yet. But the NOAA, the National Oceanographic and Atmospheric Administration, which oversees the Fish and Wildlife Service, is disputing whether the dredging has been enough. And there's a bit of a dust-up going on between the EPA and NOAA. There's also a natural resource damage assessment underway where the trustees, which are the Fish and Wildlife Service, NOAA, and the New York State Department of Environmental Conservation, they are trying to recover damages from General Electric to pay for the restoration of some of the natural resources in the Hudson River. And as I mentioned before, the Upper Hudson River is one of the few places on Earth where we know that bacteria were really going after PCBs and trying to destroy them. That's where we first learned about it, where we learned much of what we know about dechlorination came out of the Hudson River. But it's important to note, all of that dechlorination was not enough to prevent GE from having to spend $500 million dredging the river. So dechlorination's nice, but it's usually not enough to actually fix whatever the environmental contamination problems are. So this is some work that we did. This is just showing how the sources of PCBs to the lower Hudson River, so this is below the Troy Dam, the Upper Hudson River flows into the lower Hudson River, this is just showing how the sources to the lower Hudson River have changed over time. I think the most interesting part of this is the right-hand panel. You take a sediment core, you stick a tube down into the sediment, and when you bring it back up, it's full of sediment, and then you cut it, and you measure the PCBs and also other chemicals in each of those different layers. And if you've taken a good core, then the layers were set down very evenly. In the New York, New Jersey harbor, that sedimentation rate is about 1 centimeter of sediment depositing every year. And so you can estimate how old these different layers are. And so where you see the big max of PCB concentration, we believe that was 1977 when PCBs were banned because they were going gangbusters right up until the very end. So the highest concentrations are probably right around 1977, and then they fall off. And the orange dot there, the maximum, that's actually Aerochlor 1248, which is not what GE was using. GE in Upper Hudson was using Aerochlor 1242. So the thing I find interesting about this is that everybody was using PCBs up until 1977. It's not just General Electric. These were all coming from New York City and the surrounding area. And the main source of PCBs to the lower Hudson River at this point was all this urban stuff coming out of the city. But then after 1977, you can see that stuff falls away really quickly. It kind of disappears. But the blue dots, which is the stuff coming from the Upper Hudson River, the Aerochlor 1242 that GE was using, it falls off more slowly. So that these days, at the top of that core, this core was collected in 2002, I think. So in present day, the Upper Hudson River is the biggest source of PCBs to the lower Hudson River now, because other things have kind of been taken out of the equation. The other stuff is washed away from the system. Here's another example. This is Spokane County, Washington. I did some work with them trying to track down PCBs in their wastewater treatment stream. And the top figure is showing the PCB congeners in their influence, what's coming into their wastewater treatment plant. And they're kind of roughly ordered from the most abundant congeners on the left to the least abundant or less abundant congeners on the right. And then below that is the effluent. What happens after the treatment process? What's actually being released from the wastewater treatment plant into the river? And what's interesting is, first of all, the two don't look the same. And the reason for that is that this wastewater treatment plant was built under a really high level of treatment, so that there's almost no solids coming out of this plant. So anything that's sticking to a solid particle has gotten stripped away. And the only thing that's left is the stuff that's dissolved. And the one PCB congener that is now dominant in the effluent is PCB11, which is the one that comes from pigments. And so this is a problem for the city of Spokane and the county of Spokane, because they can go after the Aerochlor type sources. They're one of the cities that's suing Monsanto, for example. They can try to remove old transformers and capacitors. They can try to do a lot of things to remove the Aerochlor type PCBs from their system, but that's not their main problem. Their main problem is PCB11 from pigments. And what are they going to do about that? That's quite difficult, because people are always going to use color printed, paper, and they're always going to wear printed clothing, and they're always going to have these pigments in their system. There's not that much that Spokane County can do about their worst PCB problem. This is a graph that's trying to summarize what I've seen across several different watersheds. So on the left, you have the New York, New Jersey harbor. Next to that's the Delaware River, and then the Portland Harbor Superfund site, and the Green Duwamish River. The Green Duwamish River runs through Seattle into the Puget Sound. And the point here is that some of these places, like especially the Green Duwamish River, you see that you've got the green, the blue, and the purple bars. Those are all Aerochlors. So the Green Duwamish River, the Seattle area, is totally dominated by Aerochlors. And that's kind of what I would have expected for the rest of the world, too. And that's roughly true for the Portland Harbor, although the Portland Harbor also has a lot of dechlorination happening, which shows up in the water column. But then you get to the Delaware River. We're moving, right to left. You get to the Delaware River, and you see that big black bar. That big black bar is due to the production of titanium dioxide at a plant in Edgemoor, Delaware. So that's a non-Aerochlor source of PCBs. And in the sediment, that's more than half of all the PCBs in the sediment are coming from non-Aerochlor sources. So I hammer on these things, and a lot of people are probably saying, oh, why do we need to learn about non-Aerochlor sources? They're not a big deal. Well, they are. In some places, they are a very big deal. In the Delaware River, they're a very big deal. The Upper Hudson River is more typical, where most of what you're finding in the Upper Hudson River is related to Aerochlors. But there are some places in the world where these non-Aerochlor PCB sources are very important. So what do you do about the cleanup of PCBs? This is very tough. There's a lot you can do in terms of prevention. And for example, the Great Lakes Binational Toxic Strategy, one of their main things is to remove and replace PCB-containing electrical equipment, especially transformers. That's the big thing that they're doing in Chicago. They're doing this in New York City. A lot of places all around the country are trying to just remove known sources, stockpiles of PCBs in their electrical grid. Unfortunately, that mostly gets landfilled, but, you do what you can. You can also try to prevent sediment that has PCBs on it from ever getting to the waterway. So, for example, that's one of the reasons why that wastewater treatment plant in Spokane was built to have such great solid removal, because they just wanted to get all the PCBs out so that the solids never even reach the river, and therefore the PCBs stuck to the solids never reach the river. There's also other things going on trying to, have stormwater management so that the particles get filtered out of stormwater before it runs into the waterway. You might be familiar with a lot of the rain gardens and things like that people use. There's in many cities, for example, I know in Camden, New Jersey, there was a big track down study where they were trying to figure out what are the PCB sources in the city of Camden to find them and cap them off. Those have had mixed success. In terms of remediation, usually if you're talking about PCB contamination in a waterway, the only cost-effective solution is to dredge the sediment, to remove it from the river, mix it with cement, pack it into a rail car, and send it to a hazardous waste landfill. That's what they did in the Upper Hudson. That's what they did in the Passaic River. That's what ends up being very commonly done. If you can't remove all the PCBs in the sediment, which you can't, there's always going to be some PCB containing sediment left over. One thing that has been tried is to add a sorbent like granular activated carbon, which is basically just soot, like black carbon. If you add that to the sediment, the PCBs sorb to it really strongly, and then even though the PCBs are still there in the sediment, they can't get out to affect the biota, the worms and the clams and the fish. So they get sequestered and they don't go anywhere. So that's another option that people have tried. Okay, so I'm going to close my talk here by just spending a couple minutes talking about the issue of PCBs in schools. Here's a picture here of Cindy Crawford talking about PCBs in schools. She's let some celebrity status to this issue because this was happening in the Malibu High School, which is where her children were going. So she got very active in this issue. So many of the public buildings that were constructed in the 1960s and 1970s had PCBs in their building materials. Mostly this was in the form of Aircore 1254, although some of the other Aircores were used as well. And they were in the caulk, especially caulk like around windows and between masonry joints. Remember, all these buildings, a lot of them were cinder block, and in between the cinder blocks, they would have a caulk joint, and so that kind of caulk. They're in the fluorescent light ballasts, and sometimes the adhesive that stuck the carpet to the floor, all kinds of these building materials could have PCBs in them. And from what I have heard and understand, the PCBs were mixed into the caulk and into the building material on site. So some construction worker who probably doesn't have any training or know anything about PCBs was told to mix some PCBs with the caulk, make it half and half, right? Something like that. So they would mix this stuff together and then they would go caulk everything. And at the end of the day, say you got a little bit left in your bottle of PCBs, you don't really want to do anything with it, you just dump it on the ground. So unfortunately, that means that the soil around many of these schools is pretty contaminated. And I know that that turned out to be the case around the Malibu school. And we've seen that PCBs can volatilize into the air. And so then they get into the dust. They go, from the caulk to the air and then onto the dust. And then the dust is all over in the HVAC system and all of the ductwork. So the PCBs are moving around the school. And I've seen instances where you had buildings where half the building was built in the 1950s and the other half was built in the 70s. But the new building has sort of contaminated the old building because of this movement of air and dust throughout the whole structure. And so humans, and especially in this case, of course, school children, but also their teachers and administrators, they can be exposed to PCBs by touching the contaminated material, the dust and the soil, rolling around in the dirt in the playground. And there's a study, really recent study that came out that showed that for children, inhalation, if they are in a contaminated school, inhalation can become an important route by which they can be exposed to PCBs. And of course, children in general are always more at risk of the kinds of developmental problems that come from chemical exposure because their immune systems are developing, they're young, so they are more likely to show the toxic effects of these chemicals than older people and adults. So the EPA, you can go on their website, they've got some advice. One of the things they say is, well, replace all your old lighting systems. And that's great because if you replace, lighting systems that are so old that they've got PCBs in them, you're almost by definition going to be replacing them with something much more energy efficient. And so this is a great thing to do regardless. And in fact, the New York City school systems have decided to do this. They're spending millions of dollars upgrading their lighting. So that's good. Reduce the potential for PCBs in indoor air by maintaining a proper ventilation system, right, which means cleaning your air ducts. And then until it can be safely removed, limit exposure by keeping children away from it. So imagine how fun that is, trying to keep children away from caulk in their school. Yeah, good luck with that. Wash the children's toys often. I have kids. I know their toys were never cleaned. I know that's true. Washing their hands with soap and water. I know it's not easy to get kids to do that. You're expecting teachers to wipe down all the surfaces with wet cloths every day. Some of these things to me sound a little unrealistic, but that's EPA's advice on what to do about PCBs in schools. The actual response, as I mentioned, in New York City, the city is going to spend $708 million retrofitting all of their lighting to remove these light ballasts over the next 10 years. Another big place where this has become an issue is Lexington, Massachusetts. In Lexington, what they did is they tried to keep cleaning and retesting. You know, they kept cleaning the air ducts and cleaning the school and retesting. And so they would clean the air ducts and they would test the air quality immediately afterwards, and the PCB levels would be way down, and they'd be very happy. And then they'd come back 3 months later, and the PCB levels had gone back up again. And so they finally realized that it just wasn't going to work. They could clean it forever, and they would never be able to get all the PCBs out of the school. So in the end, Lexington had to build a new school. And we all know how difficult it is to raise the money to get that to happen. So Lexington is also suing Monsanto for the cost of this new school. And so this is a quote that I think really sums it up. If the system can't fix a problem in Malibu, California, where Cindy Crawford's kids were going, then it's hopeless for places like Louisiana or Arkansas or rural Ohio, where you don't have the money, you're not necessarily environmentally aware, you don't have celebrities like Cindy Crawford to raise awareness, and it becomes very, very difficult to figure out what to do about this. And I looked up a couple of statistics. As of 2012, the average age of a school building in the United States was 44 years, which means the average school in America was built in 1968, and therefore could very well have PCBs in it. Of course, all these schools were being built in the 60s and 70s when all of the baby boomers, were starting to go off to school, off to elementary school and off to high school. And in case you were not aware, school buildings are more than 99% funded at the state and local level. So if you have a problem with PCBs in your school, it's your problem. The federal government's not going to help. So that's obviously a big flaw in the design here. Okay, so these are some of the references that I cited throughout the talk. I hope that you've learned something interesting. I pretty much nailed my time target. It's 12:58, excuse me, right now. And I'm happy to stay here and answer a few questions if anybody has anything they'd like to ask. Yes, okay, so we have a question here about, does added chlorine to wash water or drinking water supply allow free chlorine to make any PCB congeners that are present more hazardous? Not that I know of. In order for the chlorine in the drinking water to produce PCBs, you need a pretty good amount of chlorine, and you need a lot of biphenyl as a starting material. And in drinking water, you just don't have that much. So as far as I know, it's not an issue of PCBs being formed inadvertently from the chlorination of drinking water. Another question? That's it? Okay, that was our only question. So we're done here. Thank you again for spending some time with us and learning about PCBs. And once again, our thoughts go out to the people of Puerto Rico and our partners down there, and we hope that anything that we can do to help them recover from Hurricane Maria, we are definitely going to do.